Hi, Mr. Richards here. Today's 8th grade Unit 1 Lesson 14 anchor problems on adding and subtracting with scientific notation. And so in problem 1, two students are presented with the challenge of adding 2.5 times 10 to the third and 1.3 times 10 to the fourth. They've just learned how to multiply numbers in scientific notation, and they try out using similar strategies. They get two possible answers, 3.8 times 10 to the fourth or 3.8 times 10 to the seventh. Explain or show to the students how both of the answers are incorrect. Well, simply, if we look at A here, one way to look at 2.5 times 10 to the third power is that it is really 2,500. One way to look at 1.3 times 10 to the fourth power is that this is really 13,000. And when you add these two up, you get 15,500. Now, 15,500 is actually 1.55 times 10 to the fourth. And so just by converting from scientific to standard notation, and then going back from standard to scientific, we can show that these are not correct. Now, what actually happened? What did they try? Well, it looks like they took this 2.5 times 10 to the third in one case. They added 1.3 times 10 to the fourth, and then just straight up added the decimals to get 3.8 times 10 to the, and just kept the fourth. I mean, that's how they got this one here. That's clearly not the same thing. It's clearly not right. Well, what did this person do to get this answer? Well, once again, if you look at 2.5 times 10 to the third, and you set up an addition problem, 1.3 times 10 to the fourth, and again, straight up add those decimals, you get 3.8 times 10 to the, they look like they took 3 plus 4 to get 7. Well, that's not the correct answer either. And you can only add this 3 and the 4 if you're actually multiplying the scientific notation. And so that's clearly incorrect. Well, why will these strategies not work? In B, what I'd like to show you here is that when examining this 2.5 times 10 to the third, as we wrote this in standard notation, that 2 is actually representing the number 2,000. That's a 2 in the thousands place when it's times 10 to the third. Versus this 1.3 times 10 to the fourth, that 1, that's not equal to 1,000, that's equal to 10,000. And so using these strategies of just straight up, okay, let's do something with the exponents, let's do something with the decimal portion. No, you can't do that when you have different exponents. And again, the key is with different exponents. Some strategies that you could use to solve these questions? Well, one is just to convert scientific notation into standard form and solving it like we did up there. I mean, you could simply do that, but there is a better way. Let's look at this and take 2.5 times 10 to the third, and let's add 1.3 times 10 to the fourth. That's our question, correct? The big thing that you need when you add or subtract in scientific notation is these exponents to be the same. In other words, that 2 was 2,000, that 1 was 10,000. I need this number to be the same. And so looking at the 3 and the 4, what I like to always do is take and make these 10 to those match the largest exponent. I'd like to make it match the largest, so in this case 10 to the 4th. So I want to take this 2.5 times 10 to the 3rd and make it something times 10 to the 4th. I'm going to end up keeping the 1.3 times 10 to the 4th. Well, what does this become? Well, the 3 to a 4 was 1 larger, a magnitude of 10 larger. So I need to make this 2.5 a magnitude of 10 smaller, and I can do that by sliding the decimal point back 1 to the left. So this is really 0.25 times 10 to the 4th. And now when I add these, since I have the same magnitude, since it's times 10 to the 4th for both, remember, this one was a 10,000, the 3 would have been 1,000. Hey, that 2 is still 1,000 or 2,000 in this case. So now it's like lining up your place values so you can have this times 10 to the 4th thing. This times 10 to the 4th thing stays the same now. And we add these decimals, 5, 5.1. So 1.55 times 10 to the 4th, and sure enough, it matches what we did there when we took these to took these to standard and simply added them. And so getting these magnitudes to match is going to be our key when we're adding and subtracting with scientific notation. Let's move on to example 2. The Great Lakes are a series of freshwater lakes located on the United States and Canadian border. Lake Superior has the greatest volume of water, with 3.12 times 10 to the 15th gallons of water. The smallest lake by volume of water is Lake Ontario, with 4.26 times 10 to the 14th gallons of water. How many more gallons of water are in Lake Superior than in Lake Ontario? In other words, we're trying to take Lake Superior and we're going to subtract Lake Ontario from this to find out how many more gallons are in Superior than Ontario. So this is then 3.12 times 10 to the 15th minus 4.26 times 10 to the 14th. Just like with adding, we need to make these 10 to the same magnitude. And once again, my advice is to make it match the largest. Well, the largest here is 15. And so I want to take this 14 and make it a 15. If I do that, I'm going up by a magnitude of 10, which means I need to make this one smaller by a magnitude of 10. And so what I'm left with here is 3.12 times 10 to the 15th, and I'm going to then subtract. This is now 0.426 times 10 to the 15th. Now it is important to make sure we don't ignore the fact that there is a 0 here. So that way when I subtract, we'll keep the 10 to the 15th, but we're going to have to do a little bit of borrowing. I'm going to borrow from this 2. This is 10 minus 6 now is 4. I have to borrow from this 1. 11 minus 2 is 9. Borrow from the 3. 10 minus 4 is 6. And then 2 minus 0 is 2. So 2.694 times 10 to the 15th gallons of water is our solution for problem 2. Once again, make sure you're getting the same order of magnitude. And you can't just change this to 10 to the 15th, making it bigger, without making this part of it smaller. 4.26 times 10 to the 14th is the same number as 0.426 times 10 to the 15th. It's the same number, just written differently. So we can subtract. Problem 3. A water molecule is made up of 2 hydrogen atoms and 1 oxygen atom, represented by, or as, H2O. One hydrogen atom has a mass of 1.7 times 10 to the negative 27 kilograms, and one oxygen atom has a mass of 2.7 times 10 to the negative 26 kilograms. What is the total mass for a single water molecule? Well, total mass on this adding and subtracting section means we're going to simply add. And we're going to have 2 parts hydrogen, 1 part oxygen. Well, let's take and get these 2 parts hydrogen first. We don't have to mess around with magnitude size yet, because if I take 1.7 times 10 to the negative 27th and add it to 1.7 times 10 to the negative 27th, right now it's the same magnitude. They're both times 10 to the negative 27th. So I can just add. This becomes 3.4 times 10 to the negative 27th. And now I have my H2. Oh, what about the O? Now I have to add the oxygen atom, which is 2.7 times 10 to the negative 26th power. So again, this was just the 2 hydrogens, added those up. Now I'm going to add in the oxygen atom. Well, to get this, we want to make it match the larger exponent. The larger exponent is 10 to the negative 26th. And so this is what I'm going to want to take to be a negative 26. And once again, that's getting bigger by 1. So this has to get smaller by a magnitude of 1. So as I go to rewrite these are 0.34 times 10 to the negative 26. And I'm adding 2.7 times 10 to the negative 26th. Same order of magnitude, I can simply keep the times 10 to the negative 26th and now add 410. Don't forget the decimal point. 1 plus 2 is 3. So 3.04 times 10 to the negative 26th kilograms is our solution. That's the last problem. But before we call it good for these notes, what I'd like to do is just to make sure we understand and review some 2 quick concepts here. So magnitudes must match in order to add and subtract with scientific notation. So it's good to just quickly re-review how you make magnitudes match. If I have something like 3.45 times 10 to the 5th, and I want to just in a course of a problem make this go to something that's 10 to the 7th, what you need to look at is to say, all right, to get from 5 to 7, this is going up by 2 magnitudes of 10, which means this portion of it has to go, if I throw in a couple zeros to the left, down 2 magnitudes of 10 to match it. So 1, 2, this is going to then be equivalent to 0.0345 times 10 to the 7th. 3.45 times 10 to the 5th is equivalent to 0.0345 times 10 to the 7th. Now that's the direction I'm encouraging us to go, taking the smaller ones and matching the larger ones. But just in case, what if you had to go to a different direction? For example, if you had 6.78, I know, creative, right? 678 times 10 to the negative 9th. And your question was asking you to go, I want this to be 10 to the negative 11th. Well, to go from negative 9 to negative 11, that's going down 2, which means this is going to have to go up 2, larger by 2, to make it match. So this would be 6.78 times 10 to the negative 9th is equivalent to 678 times 10 to the negative 11th. And again, that's just to move them back and forth and whatnot in the course of solving questions here. So making the magnitudes match is a must. Being able to go and make 3.45 times 10 to the 5th up to something like times 10 to the 7th is a skill you need when adding and subtracting with scientific notation. And so again, same magnitudes when adding and subtracting. When you have something like, let's say, 3.45, be creative again, 3, 4, 5, times 10 to the 5th, and we're going to add 6.78 times 10 to the 7th. So look for the larger one. The 7 is larger than 5. Make both magnitudes equal the larger. Okay, you want to make both magnitudes equal the larger. That's what we're trying to do here, which means this 10 to the 5th needs to go up 2 to get to 10 to the 7th. Okay, which means then that this portion is going to have to go down 2 to make it match the up 2, or offset the up 2. So this then becomes 0.0345 times 10 to the 7th plus 6.78 times 10 to the 7th. Now we can add. You keep the 10 to the 7th, 5, 4, 11, 8, and a 6. 6.8145 times 10 to the 7th. And so hope the 3 examples were helpful. Hope these little bonus examples were helpful, because the key with all of this stuff is that your magnitudes must match in order to add and subtract with scientific notation. You need to be able to manipulate these numbers to make these magnitudes match before you add and subtract in scientific notation. And so that's it for this lesson. It was 8th grade, Unit 1, Lesson 14. Good luck.